MPP LV6048. Pulling 10 amps on the battery. It's 9 o'clock at night. There's no solar input. .48 volts, 137 amps on that voltage. LV6048. So far I'm pretty happy with one. So I think I'll get another. We've been running the house pretty normally now for about a month. We've gotten our first utility bill, but it was only half month when I turned it on, somewhere in the middle of the month. And it was about $130 cheaper. And so far I'm pretty happy with it. I just finally got around to putting an oscilloscope on this inverter's output, and I'm happy. I'll show you that here in a moment. But first, a little update is all the panels are done. Everything's wired up. So I've got the grid panel, which is a 200 amp with pass-through lugs. This is where all you on-gridders like to go. So this is on. Then I have a 50 amp pass-through, which goes to this outlet right here, which the inverter is plugged into. It only pulls from this if I overload the inverter, which happens probably a couple times a week when the wife's running the electric oven, the electric stove, and then, you know, kicks on a washing machine or something, and it'll switch over for a little bit until the load comes down. But that's there. It's on this breaker. This is a spare breaker, and this is the one outdoor air conditioning condenser unit. This is the other outdoor air conditioning condenser unit. The house was built in 1908, so there is no way to get ductwork from the first floor to the second floor. So when they redid the house, 2010, they just put in 2 units, one in the attic and one in the basement. Works pretty good. You get 2 zones. You can set the temperatures. You don't have to keep the whole house warm. With utility bills coming to be what they are, that's probably good. We've got the main, what do we call this? The critical loads panel, even though it's literally everything except the air conditioners I pulled off here. It used to be down here, so I moved some stuff around. But there's the interlock switch, so you can't accidentally turn on the main while the generator's on, and vice versa. It's marked generator because that's the way it used to be, so now we'll just call it solar generator or diesel generator. And I can select how I want to power this breaker to feed the house with either the solar or the generator, or both at the same time. So right now, this is going up into the panel. Oh, I'm sorry. This is going up into that panel. And from this panel, we have another interlock. This interlock will pick to either pull power from the solar or from the diesel generator. Obviously it's set on solar right now, but I gotta label this stuff up too. What's this other panel? This other panel is a generator sub panel. So I've got the generator coming in here, then one breaker feeds this, so I can select between solar or diesel. The other breaker then goes down to that other plug. This way, if it's a grid down situation and it's been cloudy, just black skies, thunderstorms for 3 or 4 days, and I'm out of battery, I'm not charging because there's no sun because it's just black skies, then I can leave all those exactly the way they are. I don't have to adjust anything. start up the generator, it would feed this outlet. I would then pull the plug out from the grid, plug it into the generator. The generator would then bypass through here and feed the house. Well, then why not just flip that switch and just run the generator right into the house? The point is, I can come in here and change a setting and then charge my batteries while running the house. And this way, when the batteries are charged, I can shut that generator off. That's not super fuel efficient. It's a big 12 kilowatt military generator. And then I can run for another day or 3 days once I get the other batteries hooked up on just batteries, right? So the generator would only have to be on when it's loaded, which is also good, prevents wet stacking on that diesel generator. So that's what all that is. These watt meters are pretty accurate. There's not a whole lot of load on right now. There's that guy. We've got the batteries in here. I do have this one cover I still got to put on. So it's that little thin panel right there. I don't have that on yet because I still have one hokey set up in here, which is, this is a shunt trip breaker. It requires 24 volts. So I have a little dingly dangly 48 volt to 24 volt converter that powers that. So if for some reason the top of the breaker loses power, then it'll shut the breaker off anyways. But either way, here's my 3 packs of batteries. Each are 128 amp hour, so that's 64 amp hour, 64 amp hour wired in parallel. One BMS, one BMS, one BMS, and they are, and then there's some spare stuff in here, and got some fire blankets sitting up here, which I'm actually gonna lay on top of all of this just in case. It's in a steel cabinet on top of that too. It's all stainless steel hardware I've been using. But I've got everything on these bus bars, and then the bus bars then feed this breaker. So the most I could pull from this is 80 amps. And I have it wired with number 4 SOW. So it's real flexible. This way I can still pull the drawers in and out if I want to. But in reality, I typically only see like 45 amps to each one of these, which is fine because this is a 150 amp breaker, and that's typically only when I see it charging. As the tag said, it was only 137 amps, but for pulling from the inverter. But when it's charging, I've even seen up to 50 amps on each one of these. So it was like, you know, right there. And when it's pulling 150 amps, these I think these are 4-aught cables. They surprisingly are warmer than room temperature. Like, you can definitely feel them. There's a box of 5 more JBD UPSs. No, BMSs. I have it wrapped in tin foil because, you know, the 24th, that never happened. But that's the one battery cabinet, and it is a battery cabinet. It was meant for lead acids for a UPS. But I'm going to take this shelf down. I'm going to finish building this shelf and put all this stuff over to here. I'm going to put a wire shelf over here, and then I'm going to put some hardy board all across the ceiling. This way, God forbid, if there's ever a fire with these, it'll hit hardy board, not wood. And you know, they're gonna go, right? There's no way you're gonna stop them. I'm gonna put fire blankets on all top of the blankets, all tops of the each battery. I'm gonna do the same thing over here, and then I'm gonna coat this in hardy board. This shelf, this one's already basically in a non-flammable cabinet already. Coat the ceiling with hardy board, and I'm thinking maybe do some sort of like a thermatically controlled exhaust fan and have them plumbed into this box and this box, so if there is ever a fire, it'll suck the exhaust gas out. And we've got 2 fire extinguishers. This one's CO and this one's dry chem. But that's the setup at the moment. It seems to be working pretty good. Like I said, I just got to put this panel back on once I mount that little DC power supply. It's a buck converter, because it's stepping it down from 48 to, we're actually going from 60 to 24. But that's the system. And then I've just stumbled across 36 lead acid batteries. They weigh 2,200 pounds, and I carried them all down here by myself with 2 of these guys. These are worth the 10 bucks I paid for them. These are, let's see on that side. Data safe Enersys 12 volt. They are 71 amp hour batteries, I believe. 284 watt cell, 15 minute. I looked them up. They're 71 amp hours. There are 36 of them, and they are brand new. They're less than a year old, and they've never been used. Problem is, this is 30 kilowatt hours. If I want these to last more than 3 years, it means I can only use 15 kilowatt hours of it, and that'd be 50%. So even then, they're only last 3 to 5 years. That's 20 kilowatt hours, and I have another 50 sitting outside that I'm going to put on the shelf. So I have 70 kilowatt hours over here. All lithium, all the same chemistry. I can't just toss these into them because it's a different voltage, different chemistry, different charging characteristics. So I don't know, maybe I'll put this in the barn on a second whole system or something. And then I've got the sump pump backup of backups. It's a 2,000 watt modified sine wave trip light inverter right there. It's 12 volt. So all these batteries are wired 12 volt. They're all paralleled. I'm taking the positive from this battery, the negative from this battery. So that negative has to travel all the way through all these 4-aught cables and back around. Same with the positive. It's got to go all the way back around this way, so it's tapped, corner to corner like it should be. So all the batteries get charged the same. And right now it's 100% charged. 0.7 amps. I doubt that's wholly really accurate, but anyhow, I'm getting off on a tangent here. Point is, it's this guy, that inverter, LV6048. Let's get to it. Let's go upstairs and have a look. I got my Tektronix oscilloscope set up over here. That ain't bad. Turn that off. It's a little flat at the top and the bottom, but that ain't bad. I'd be willing to call that, like less than 10% total harmonic distortion. Maybe even 15% total harmonic distortion, but I'm okay with that. Now, there's not much load on it. So let's add a load. Let's just had dinner. Let's turn the big one on. Okay, that's on. Let's see what the sine wave looks like. Probe. actually got better under a load. The flats went away.